Dillon Jaglal is from Melbourne University. So Dillon is a PhD student in smart grids at University of Melbourne, Australia, where he's working with residential battery energy storage and investigates the role in frequency regulation. He holds a Master of Science with distinction from University of Manchester in UK and a Bachelor of Science with honors from University of the West Indies in Trinidad and Tobago. Dillon, thank you for being available. The stage is yours. I will let you share your screen and start. Thank you.
Can you guys see my screen?
Yes, I do. Thank you.
Hello and good day to everyone. Let me welcome you as I share my work with you today. My name is Dillon and I'm with the University of Melbourne. This work was done in collaboration with Dr. Procopiou, Dr. Petrou, and Professor Ochoa, who are also with the University of Melbourne. So this is the outline for today. First, I'll give an introduction and discuss some key aspects with PV generation and batteries. And to understand the concepts with PVs and batteries, in this context, I'll give you an illustration of how they work. Then I'll present the methodology of how we developed a bottom-up approach, and then assess the scenarios to understand the effects with system-level generation costs. And then finally, I'll present a case study with some of the results, and then I'll conclude. So we know that residential PV systems are on the rise, and as a matter of fact, we are seeing here in Australia a large adoption at the residential level, and this is due to their declining cost and because customers wanting to reduce their electricity bills. And also, we're seeing that the adoption rates of batteries are also falling for the same reasons, and customers want to make more of their PV systems. On the right-hand side here, there's an animation showing as PV penetrations increase, we see this duck curve forming at the system level, and the net demand is being reduced. And we know that this can cause issues at the system level, since the generation needs to ramp down because of the PV generation and then ramp up again later in the evening. In theory, batteries can absorb this excess PV and reduce these duck curve effects. However, off-the-shelf batteries, I'll discuss what these off-the-shelf batteries are later on, they're used for self-consumption. And at times the absorption can be limited and the extent it is unknown. So now I'll give you an illustration of the batteries and PV systems. So we have 4 plots on the right-hand side, A to D, where A just shows the load demand and the PV generation profile, and plots B, C, and D corresponds to PV only, off-the-shelf, and adaptive decentralized AD. So first I'll begin with PV only. So you can see that because of the small load demand, the PV is being exported into the grid. And then we know that these exports can cause some technical challenges to the distribution network. For example, they can cause voltage rise, and then when adopted on a mass scale, they can cause system level impacts such as the duck curve we just discussed. Then if we look at the off-the-shelf case, this is modeled for self-consumption, and the principle of operation is that when generation exceeds demand, the batteries start charging until they become full. Then when they become full, they export the excess PVs back into the grid. And then later on in the evening hours, when we don't have PV generation, they discharge to cover local demand. And what we can see is that when the batteries become full, there's a large amount of exports being sent back into the grid. And as a matter of fact, this exports is very comparable to the case of PV only because the batteries become full. And then finally, we have the AD, or Adaptive Decentralized Control, which was developed by some colleagues of mine here at the University of Melbourne. And it's aimed at distribution networks to overcome these impacts of large PV exports. And the principle of operation is that it adapts the charging power proportional to PV generation, significantly reducing that PV exports. And what we can see is that from this hashed area here, we can see that the exported power for the case of AD is much less than the case of OTS and PV only. So now we ask the question, what is the effects of this if adopted on a mass scale? How would it affect the system level net demand and then the cost? And how do we model this from the household level all the way up to the system level? So this is the methodology we employ to carry out the study, and then I'll kind of walk you through this right now. So First, you select an operation schema and penetration level, and then you can start building up the demand profiles using these equations on the left-hand side here. So depending on the scheme, OTS, AD, or PV, that determines this term here, which is the power of the battery. And then you can get the demand for the customers with battery. Then you can sum all of these demands, which is corresponding, which makes up of customers with demand only, customers with PVs, customers with batteries, again from here. And then finally, there's a non-residential component. We need to sum all of these together to get the system level net demand. When we have the system level net demand, we can then run the unit commitment, and we're using a basic unit commitment, and it considers things like the production costs, the startup costs, and the shutdown costs. We can run the unit commitment, store all of the generation status, the dispatch, and then repeat this process for how many penetration levels we're doing, and then we can perform the assessment. So this is the case study we're going to analyze here today, using the methodology we just presented. We have 6 base load plants, which are coal-fired, with the sizes here, 2 larger gas OCGT plants using for more flexible for peaking, and then 6 smaller plants, again, gas OCGT, which is used for peaking. To have an idea of the size of the total generation capacity, it's around 600 MVA, and it's based on the modified IEEE 9 bus we use in our studies. For the customers, we have a total of 73,000 residential customers. And for the PV system, they're based on Australian statistics from March 2016 onwards. And the size range from 2.5 to 8 kilowatts, with the majority of them being around in this 5.5 kilowatt range. For the batteries, it's based on Tesla Powerwall 2, which has a power capacity of 5 kilowatts and an energy capacity of 13.5 kilowatt hours. And for the penetration levels, we're going from 0 to 110% intervals, making 11 penetration levels inclusive of 0. And then 3 here comes from the 3 scenarios, PV only, OTS, and AD, giving a total of 33 scenarios. So firstly, let's look at the system level net demands. And immediately you can see visually that, so we have the 3 cases here again, PV only, OTS, and AD. Visually, you can see that we have very similar net demands for PV only and OTS. And this is because, as we've shown in the illustration on my 3rd slide, I think it was, when PVs start generating, the batteries become full quite quickly. And then when they become full, all of that exported power is sent back into the grid. That exported power back into the grid is reflected here in the system level net demand. And then for this day, at least, that we're presenting here, we have very similar net demand profiles for PV only and OTS. And then for AD, where the operation is to reduce this peak exports from PV, and again, aim a distribution network distribution networks. So by reducing that peak exports from the PV on a large scale from all the customers, it's being reflected here. And we have a lot of a more flatter behaving profile. My colleagues call this instead of calling it the duck curve, they call it the platypus curve, because we have platypus here and it kind of looks a bit like it. It's a bit funny. So now we have the net demand profiles, we can run the unit commitment. So these stacked area charts shows for the 3 cases, and then immediately you'll notice that there's no plot for, so it goes from 80, 90 to 100%. Immediately you'll see there's no plot for 100% PV, and that's because the net demand reduced to the level where the minimum stable generation constraint of the units have been met, and then no solutions existed for that time. These shades of gray shows for the base load plants, the 6 base load plants, and then these warmer colors and green shows for the gas peaking plants, and then this blue area here shows for the batteries. So firstly, we can see that in the evening hours here, we have reduced gas generation for OTS and AD, and that's because of the operation of the batteries. They're covering the local demand of the customers, and because they're covering that local demand, we can see that less gas is needed here compared to the case of PV only. if we look at the baseload units, you can see that there's less severe ramping for OTS and AD. And that's because of the inherent operation of the batteries. They're charging a little bit of that PV generation, much more for the case of AD, but they're charging that excess PV generation, and then you're seeing that system level net demand still being there. You can see that baseload plants are still on. Then finally, if you look at, again, so the gray shows for the baseload plants, you can see that some of the plants switch off here for a certain amount of time, and then they have to switch back on again in the evening. So we have this start-stop operation, which led to some interesting results. And then when you look at the case for AD, we can see that no baseload plants go offline because we still have that underlying demand, and we're using a lot of that cheap generation during the day. So now we have an understanding of what the dispatch looked like for this day for the plants for the three schemes being considered. Let's look at what the cost looks like. So I kept the dispatch here on the bottom left to walk you through and understand what's happening on these curves that I'll present now on the right. So we have three plots on the right-hand side showing the energy for the two types of plants, coal and gas. And for each operating scheme, PV only, OTS, AD, and then for each penetration level. Then we show the total daily cost. And then we have the average cost per megawatt hour. And the reason we show this is, oh, by the way, this was averaged across the generators throughout the 24-hour period. And the reason we show this is to capture the effect of the unit cost of energy delivered. So let's walk through the previous results and see what's happening here. So firstly, we have this reduced gas generation on the evening hours here. And because we have that reduced gas generation, they're expensive, we can see that's being reflected in the cost. So you see this cost reduction as we go on for OTS and AD. Then we spoke about the ramping, where we had the baseload plants being ramped down during these PV generation hours. Because we have that baseload plants being ramping like that, we have further cost reductions for the case of AD because we're using more of the cheaper baseload plants. And then finally, we spoke about the start-stop operation of the coal plants, where we had these plants turning off here because the net demand reduced to this level. Because these plants had to shut off and then turn back on later in the evening again, they incurred the shutdown and startup costs that we presented in unit commitment. And then because we incurred these additional costs, it's being reflected here in the total cost and the average cost per megawatt hour. Then we can see that we have this reversal trend in cost as we go to very, very high penetration levels for the case for PV only, although we're generating less energy from the plants. And that's because the cost reduction from reduced energy, it's not as much to outweigh the operational cost of the generating unit. And then finally, if we look at the AD control system from compared to the rest, we can see that we have this for greater than 50% PV penetration, we have this great reduction in cost. So it has the best performance overall. So finally, to conclude, excess generation from PVs, they reduce the aggregated net demand, and this causes a duck curve. We've discussed some of the issues associated with the duck curve. In theory, these off-the-shelf batteries, they can reduce excess PV, but not always. They can become full at times. By modeling them properly, we can have a more accurate outlook on what these net demand profiles would look like, and then the effect this would have on cost. And from the results that we've presented here today, commercially available off-the-shelf batteries, they still lead to these duck curve effects because, again, they become full. And finally, I presented the AD control, what we call smarter battery controllers here. They can provide a lot of benefits in the long term, and this work is, we aim for this work to help system operators and distribution companies to combine their coordination efforts to create a better future with more batteries and PVs coming online. And with that, I'd like to thank Dr. Procopiou, Dr. Petrou and Professor Ochoa for their help with this work. And I would like to take your questions. Thank you very much.
Okay, thank you, Dillon, for your nice talk. So we have a question from the audience. So I'm not sure whether you can see it, but in any case, I'm going to read it to you, also for the benefit of all the others, and then you can answer live. So Rogier is asking that the largest percentage of penetration of PV resulted in an unfeasible unit commitment. Why didn't you allow to curtail the PV generation?
Oh, thank you for the question. Yes, we can curtail the PV and get a solution for that PV only term. But remember, what we're trying to do here is just understand the effects of how the PVs, when adopted on a mass scale, how they affect the system level generation cost. So if we altered the operation of the PVs, then we won't have a true representation of what we wanted to show here. We just wanted to see how the cost will be here. So yeah, if we alter the operation, it won't be theoretically PV only. It would be PVs with some sort of control.
Okay, there is another question from the audience, from Rahul Gupta, and he's asking, is stating that a major problem with a high PV penetration is related to congestion in transformers and the lines, voltage violation, and so on and so forth. So are you accounting for that in your control strategies for distributed batteries, or no? So are you accounting for grid constraints essentially in your distributed control action, or is something that you're not considering yet?
Okay, so I'm seeing a question here. So
all right, okay, maybe you can.
Yeah, so we're not running a power flow model here for the unit commitment. We're generating the profiles using the schemes, but just the profiles. We're not running a power flow for this case here. So I can't say much about that. So let me read the question for the audience because it's being recorded. Major problem with high PV penetration is related to congestion in the transformers and lines, voltage violations. To account for those, what kind of power flow model you use, and can you talk about their computational performance? So yeah, we're not running a power flow here, so I can't.
Okay. Well, I guess the sense of the question is more the fact that, of course, like when you have like a lot of in-feed from PV generation, you might generate constraints violations in the distribution network. So I think the sense of the question is whether at the current stage you're accounting for that, or if you are just implementing only some sort of self-consumption mechanism, I think. But in my understanding, this is what you're doing.
Yeah, we're not.
At the current stage. Yeah, you're not considering grid constraints at the current stage. Okay, thank you. So we have another question, and maybe this can be the last one. So Matt Dekin from Newcastle University is thanking you for your presentation, and also is asking whether you can tell us a bit more about if and when you might expect these sorts of problems to exist in the Australian systems. Are there already issues with off-the-shelf systems?
So a lot of work from my team is actually being produced on this. I will really be happy to point you to some of those papers. And yes, we are seeing some problems especially at the medium voltage level. Not so much on the voltage side, but more on the thermal side at the medium voltage level. And to answer the question of when, we're seeing it around between, I'd say from my memory, I'm calling from memory here, between 30 and 50% PV penetration. Bear in mind, right now we're at 20% more or less.
All right, thank you, Dillon, for your nice presentation and for replying to all these questions.